Liquid is the one which is having intermolecular forces of attraction very much less than that of the solids but greater than that of the gas. The force of attraction, that is intermolecular distance, is then that is very much greater than that of its size. Velocities is given as velocity root mean square velocity is given as square root of mean of square of the molecules. Hello everyone, I'm Brinda from Department of Physics, welcoming you all to Chapter 13, Session 1, and chapter name is Kinetic Theory of Gases. So in today's class, we are going to study about theory of gases. So you all know that what is solid, what is liquid, as well as what is gas. So solid are the substance whose molecules are closely packed, so its intermolecular forces of attraction is too very high. And liquid is the one which is having intermolecular forces of attraction very much less than that of the solids but greater than that of the gas. But in case of the gas, you can see here it's freely moving particles are present over there. So kinetic theory, why exactly this is used? Kinetic theory, it explains the behavior of the gas. That is, the idea that the gas consists of rapidly moving atoms of the molecules, you can see here, and this is possible as the intermolecular forces of attraction, which are short range forces. Okay, so the force of attraction are known as short range force, and this force of attraction lies between the molecules, which are very important in case of your solids, liquids, but can be neglected in case of gases because the molecules of the gases moves freely. Okay. So now in this chapter, we are going to study about the laws of the gas. There are certain laws called as gas laws as well as ideal gas equation. As you all know, it is PV is equal to RT gas equation we have studied in the previous chapters. Having that concept, we have to make use of and study the kinetic energy as well as temperature differences of the gases, that is its relations, degrees of freedom, law of equipartition energy. All these concepts we will study under this chapter. So first of all, let us go with mean free path. So what exactly is a mean free path? First of all, the average distance of a molecules which travel without any colliding is called as mean free path. That is, as you can see in this picture, there are particles, gas molecules are present, which is blue in color. So when it travels from this point, you can see there is a first particle here and the second particle here. The particle 1 travels in this path, that is the arrow mark, and it collides with this path, this particle called as particle 2. Before its collision, it travels from this length to this length. Now that distance, that is before another successive collision, the time taken by a particle to travel, that path traveled is called as free path. It has got no obligations in between, so no barriers in between, so it has traveled freely. That is called as free path, and the average distance traveled between the successive collisions is called as mean free path. So that is all about your concept. So atoms are much freer in gases, that is why they can travel longer distance without colliding with each other. So next we are going to study gas laws such as Boyle's law, Charles' law, as well as Gaylak's law. So we have Boyle's law. So what do we study here? Boyle's law here, in this case, it is isothermal process, which means to say the temperature is said to be constant. So what happens to your pressure? The volume is inversely proportional to pressure. So PV is equal to constant. So this holds good for your Boyle's law, same as that of your isothermal process. So the variation of volume with respect to pressure is inverse. So as the volume increases, your pressure decreases. That is what we study here in case of this law called as Boyle's law, which is one of the most important law, as well as this expression is also important to go further with the rest of the derivations. So next we are checking on to Charles' law. Charles' law is with respect to pressure remaining constant, which means to say your volume is directly proportional to temperature, where pressure is said to be constant. So you can rewrite this as V by T is equal to a constant term. And graphical representation of this Charles' law is you have X, and Y, it is as your volume increases, your temperature also increases. This is how the graphical representation shows, out of which this expression of yours is very much important along with this law. Next, we are going on to Gay-Lussac's law. In this case, we keep volume constant. So here we have constant volume. So at constant volume, your pressure is directly proportional to temperature. So we have P by T is equal to constant. So this is one set of equation which is actually again important. Again, when you plot the X and Y graph, you have P as well as T. As one variable increases, the other also increases because it is directly proportional to each other. So this is one of the other important concepts. So you need to understand the Boyle's law, Charles' law, as well as Gay-Lussac's law. What are the components, which quantity is kept constant and which quantity is varied. All these concepts will have to understand in order to study the behavior of the gas. That means to say, under behavior of the gases, we are going to study how exactly it behaves with respect to kinetic energy as well as temperature. Let us see now. Having all these three laws, let us just derive the ideal gas equation. So in order to derive this ideal gas equation, first of all, we will have to consider Boyle's law. Then we will have to consider Charles' law concept. So let us just write down here. So Boyle's law, we had a concept of PV is equal to constant, and Charles' law we had a concept of pressure is constant, so V by T is equal to constant. So these two are the terms what we have to know. So first of all, let us consider a gas. 1 mole of a gas is considered. So we have to give an ideal gas equation for it. So suppose there is a gas for which Boyle's law is applied, which means to say the temperature is said to be constant while the rest of the thing starts varying. So we have PV, temperature is constant here, remember. So first of all, we are going to start up with Boyle's law. At constant temperature, the pressure as well as volume of the gas varies. So P1, V1 will be equal to P2, and it is V2 instead of V2, I'll write it as V1 dash. P and V both have changed here at this condition. And the same gas, after its first change, at constant pressure, we have V1 dash divided by T1, because volume is V1 dash now. Same gas we will just continue. So first volume is V1 dash, and with the first temperature is equal to change in volume is said to be V2 divided by change in temperature is T2. So it's getting changed to the rest of the thing. So now on equating this, we can rewrite this as V1 dash is equal to V2 into T1 divided by T2. So let us substitute V1 dash expression, substitute the star expression in equation 1. So P1 V1 is equal to P2 of V2 T1 by T2. Let me get a T1 the other side. So I have P1 V1 by T1 is equal to P2 V2 divided by T2 is equal to a constant. So we can just take it as PV by T is equal to constant. The constant term can be represented as R. So PV is equal to RT. So this is your ideal gas equation, which is one of the most important component. This is just for if you just take 1 mole of a gas. Suppose if you consider for N mole of gas, then your equation turns out to be PV is equal to N mole of a gas to RT, where R is called as a universal gas constant. So this is one of the most important equation for you to derive rest of the derivation. So now let us just check within this behavior of the gases, we will have to check what is the relation between your kinetic energy as well as temperature. So now let us check behavior of the gases with respect to this kinetic energy and temperature. So we have to get pressure of the gas. So there is a pressure of the gas equation. So it is P is equal to 1 by 3 m by v into v bar square. Okay. So even you can write this as mass by volume is nothing but density. So 1 by 3 rho v bar square. So you can use this equation as the pressure equation. Carrying the same equation, you can rewrite this as P, your V goes to the numerator towards the left hand side. So PV is equal to 1 by 3 m V bar square. So since we know that PV is equal to RT for 1 mole of a gas, we can take this as RT is equal to 1 by 3 m V bar square. So m V bar square becomes 3 times RT. So relating it with the kinetic energy is what we'll have to check. So we have kinetic energy is equal to half mv square. So this kinetic energy, we can rewrite this as kinetic energy is equal to half of mv bar square is nothing but your 3 RT. So you can write this as kinetic energy is equal to 3 by 2 RT. So equate this kinetic energy equation with respect to this. So we have 3 by 2 RT divided by half of mv bar square. So divide this equation throughout by Avogadro number. So we have 3 by 2 R by Na into T is equal to half m by Na into v bar square. R by Na and m by Na has got one simplified equation. So we have 3 by 2 R by Na is nothing but Boltzmann constant into T is equal to half into m by Na is nothing but your small m as well as v bar square. So by this equation, we can make out that this equation lies out to be a kinetic energy. Kinetic energy is equal to 3 by 2 kBT. So here lies like energy is directly proportional to its absolute temperature. So this is the relation we just check in the behavior of the gases concept. So now behavior of the gases concept. So now let us study about the assumptions. Okay, assumptions, or it is also called as postulates of gas, kinetic theory of gas. Okay, so now let us just see here. All molecules, these are the important postulates what you have to learn. All molecules are identical in shape. Okay, all molecules are identical. And next is size of the molecules is smaller than compared to that of the intermolecular distance. The size of the molecules will be very much smaller when it is compared to the intermolecular distance, because in a container, if you just put a gas-filled container, the molecules are free to move in a random motions. So it does not have greater intermolecular force of attraction, but the force of attraction, that is intermolecular distance, is then that is very much greater than that of its size. Molecules behave as a rigid and it is perfectly elastic sphere because it has a collision every now and then. Molecules have random motion and its velocity increases with increase in temperature. As its velocity increases, its temperature also increases. So velocity is directly proportional to temperature concept we can study over here. Next we have root mean square velocity of the gases. So what is it? It is the square root of mean of squares of the velocities of the individual molecules. So velocities is given as velocity root mean square velocity is given as square root of mean of square of the molecules, individual molecules, square of the velocities, it's given here, square of the velocities of individual molecules, different other molecules. So after each you are adding up. Okay, so this is the equation. By reading the definition, we have given this equation, which is one of the most important concept. VRMS is equal to square root of mean of squares of the velocities. Okay, so this is your root mean square velocity of the gas. So now we have half mv square is equal to 3 by 2 RT. So your 2 gets cancelled and V is the velocity of RMS value. So V RMS turns out to be root of 3 RT divided by M, or this can also be written as VRMS is equal to root of 3, RT is nothing but it is P, your PV. PV is equal to RT where V lies here, so P stays there. So M is nothing but the mass, so we can consider its density. Either we can consider this or this. This is the RMS value of the gas molecules. Next we are going on to the degrees of freedom. So here what we can study, number of independent ways in which the particle of the medium can take energy. Why does it has to take energy? Because the molecules of the gas has to move freely. So in what ways it takes up the energy is what we study. Here we consider monoatomic gases, diatomic gases and non-linear triatomic gases over here. So for a monoatomic gas molecules, the degrees of freedom, you have degrees of freedom with respect to, it is a sum of translational motion as well as rotational motion. Two motions we'll have to consider, wherein in degrees of freedom for a monoatomic gas, it has got 3 translational motion with respect to x, y and z axis and 0 rotational motion. So degrees of freedom is 3 in case of monoatomic gas molecules. So in case of diatomic gas molecules, your translational motion is 3 plus your rotational motion is 2. So you have 3 plus 2 is equal to 5. In case of your triatomic, non-linear triatomic gases and all, you have F is equal to T plus R, that is T is nothing but translational motion, that is, it has got 3 translational motion and 3 rotational motion. So you have the degrees of freedom set to be 6. That is about your degrees of freedom in case of your monoatomic, diatomic as well as triatomic gases. So now you have, with respect to this degrees of freedom, something called as law of equipartition energy. So for this, for a dynamic system which is in equilibrium, the energy of a system is equally distributed among the degrees of freedom of a molecules. Okay, so energy whichever is there, it is being equally distributed to certain degrees of freedom individually. So such concepts comes under this law of equipartition energy. The energy is equally partitioned with respect to certain degrees of freedom is called as law of equipartition of energy, and each degrees of freedom per molecule, that is equal to half kBT. So for a monoatomic gas, if you just check, the degrees of freedom is 3 and each degrees of freedom will have the energy equal to half kBT. So half kBT is equal to, we can write 3 by 2 kBT, or kB can also be written as R by Na. Next is, for diatomic gases, you have 5 degrees of freedom and half kBT, which is equal to 5 by 2 kBT. For triatomic gases, you have 6 degrees of freedom and half kBT. So 2 1 time, 2 3 times it goes. So you have 3 kBT. So this is all about how exactly the law of equipartition energy holds and how the degrees are distributed with respect to monoatomic, triatomic and diatomic molecules. So in today's class, we have studied about the kinetic theory of gases chapter, in which we have covered up the kinetic theory, that is postulates or assumptions, Boyle's law, Charles' law, Gaylak law, as well as the relation between kinetic energy as well as its temperature, and then what is its pressure, pressure in the sense pressure of a gas formula. Having it, we have derived with respect to this root mean square value, as well as we have studied the law of equipartition energy, having this degrees of freedom of monoatomic, diatomic and triatomic gases. Let us all meet in our next upcoming session with the other chapter. Until then, have a good day. Thank you.